Bismillahirrahmanirrahim. Assalamu alaikum viewers, welcome to my maths club. In this video we are going to discuss the last four types of our L'Hopital's rule of indeterminate forms. So we are going to pick up few examples that are going to represent all these four types one by one and try to discuss them exhaustively. So once when we try to pick up an example that is going to represent this type, so let's see how we are going to handle that. Of course, we are going to use the basic L'Hopital's strategy of differentiating the function once when we apply the limit and find the indeterminate position of it. So that's what, of course, we are going to apply. So let's see the example now without wasting time. Further ahead. So here you go, the example. Okay, so this is it, our nice beautiful example. So first of all when you apply limit x tending to 1 on this function, which is the product of a polynomial and trigonometric functions. So once when you apply the limit directly on this product of two functions, what type you're getting? So if I just try to do it in rough over here just to make you understand. So once when I apply the limit here, and at the place of my x I'm writing 1, so I'm not writing anything, it means. So this is actually 0 and tangent 90, pi by 2 is actually 90 degrees, you know that. So once when you do this, tangent of 90 degree is infinity, so it is giving me this type 0 into infinity once when I try to apply the limit. So that's why I'm not going to apply the limit, because I know it is giving me this indeterminate form. So that's why what I do, I simply write it like this, that limit when x is tending to infinity on this product of two functions, which is giving me one function. So it is giving me this type 0 into infinity. Okay, so I want to get rid of this. Let me just remove this. So I want to get rid of this condition. So what I do, I'm going to apply differentiation, of course. So in order to apply differentiation in the L'Hopital's rule, as I told you in the previous video, in the part 1 and 2, what we do, we need functions in numerator and denominator form, right? So I have to transform this type in the form of a fraction. Okay, I need a function in the numerator as well as in the denominator. I need that design actually. So I need to transform this original function. So what I do, I'm going to pick up the reciprocal of my cotangent is actually tangent. So I'm going to write my tangent pi x by 2 as 1 upon cotangent of pi x by 2. Okay, so first of all I give it this form. Like that. Okay, so once it is now in a perfect order to apply your L'Hopital's rule strategy of differentiation, now I'm going to apply the derivative. Okay, because I can see that if I apply limit on this type, still I'm going to get an indeterminate form, which is what, if I do it in rough, it is 1 upon 1 minus 1, and this is cotangent of pi by 2. Okay, so pi by 2 cotangent is actually 1 upon tan pi by 2, which is tan 90. So it is giving me 0 upon 1 upon infinity, which is actually 0 upon 0, right? So I'm not going to show this whole working, of course. I will simply write the indeterminate form, which is this. Okay, now I'm going to use the L'Hopital's rule of differentiation. Fine. So what I do, I will derivate my numerator and denominator separately. So I simply write my limit. Derivative of 1 is 0, derivative of x is 1, so it is giving me minus 1 actually. That's it. Okay, and the derivative of my cot is negative cosec square of this angle. So it is negative cosec square of this angle, and then of course I'm going to take the chain rule on this angle because it is not simply x. So once when I do this, I'm getting a type simply pi by 2 times this cosec square pi x by 2. So it is giving me a type, and this negative will get cancelled. So I'm getting 1 upon pi by 2 cosec square pi x by 2. Now if I try to apply my limit now on this form, what I'm going to get? So if I just move my working a little above, okay, it's here. Alright, and I know that sine of x is 1 upon cosec of x. Yeah, so I can write this cosec square pi x by 2 as sine square pi x by 2. I can write it like this. Sine square pi x by 2 upon pi by 2. That's what it is. Now once when I apply the limit here, so you can see in rough that sine square of pi by 2 upon pi by 2. So I know that sine 90 is 1. So 1 is square is 1 upon pi by 2. So it is giving me a normal value. It is giving me a real number form. So I'm no more getting indeterminate form now. Okay, so once when I apply the limit now, so I need to show my full working over here, and I will see what exactly this limit is actually giving me, what value it is giving me. Okay, so I'm going to show my nice working here now. So it is pi sine of 2 whole square upon pi by 2, and it is giving me 1 square upon pi by 2. So finally I'm getting this. This is going to be my answer, and I'm going to stop my work here. So that's how you handle the indeterminate form. Now we are going to pick up our next example, which is going to deal with this type, infinity minus infinity. That's what we are going to discuss now in this next example. So let's see what exactly the example is. Okay, so this is our next example, and once when we try to apply our limit directly on this function, what form we are going to get now? Okay, so we are going to check it in our rough section over here a little. So you see, once when I apply the limit, it is 1 upon 0. Whenever I'm having x, I will just replace it with my 0, just like that. So 1 upon 0 is infinity minus 1 upon 1 minus 1. This is still, it gives me 1 upon 0, which is also infinity. So I'm getting this type, infinity minus infinity. So once when I monitor this situation, I come to know that it's not giving me a definite limit value. So of course I need to make some adjustment. I need to apply my L'Hopital's rule. So how about if I just take LCM of this function, and then I try to apply the limit and then see what kind of form I'm having. Either it is indeterminate or a proper definite order. So let's see what we are having. So if I just apply my LCM work here, LCM of my two different factors is actually the product of two different factors is my LCM. So I'm going to write x times exponential x minus 1. This is actually my LCM. So that's what I'm having. So once when I apply limit here, what I'm going to get, it is let me just remove this part. It's going to cause mess if I keep it over here. So I must remove it. So now I have just done that, and now I'm going to apply my limit on this new form, this one. So it is e power 0 minus 1 minus 0 upon 0 times e power 0 minus 1. So it is giving me 1 minus 1 upon 0 times 1 minus 1. So it is giving me 0 upon 0. So 0 upon 0 is still indeterminate. So what to do? We are going to take our derivative. Now we are going to differentiate our numerator and our denominator one by one. So, and after that we will apply the limit once again and see what we get. So once when I apply derivative on the numerator, derivative of my exponential x is exponential x itself, derivative of 1 is 0, derivative of my x is 1, because I'm differentiating with respect to the original variable that is so discussed here. So it is x. So that's what we are doing. So okay, now in the denominator what we are going to do, we are going to take the derivative of product of two functions. Okay, so here first function is x, another function is ex minus 1. So derivative of x is 1, derivative of first function into second function as it is, minus derivative of my second function into first function as it is. That's what it is. Okay, so it is giving me a form e power x minus 1 upon ex minus 1 minus x power ex. Okay, so that's what I'm having. Once when I apply limit now on this type, what I'm going to get, let's see. So it is e power 0 minus 1, e power 0 minus 1 minus 0 times e power 0. So we are getting 1 minus 1 upon, this is actually 0. It is 1 minus 1 minus 0. So still I'm getting this form. Still it is indeterminate. Okay, no issue. Let's try to differentiate numerator and denominator once again. So we have to keep on going. We have to keep on repeating this L'Hospital strategy till we get a unique answer once when we apply the limit. So now the derivative of ex is ex itself, derivative of 1 is 0, derivative of ex is ex itself, derivative of 1 is 0, and then over here we are going to differentiate with respect to the product rule. So it is giving me ex minus x times ex. Yeah, so that's what we are having. Okay, one blunder I did, I just applied negative sign here by mistake. This is the product derivative, so we should write positive sign here. I wrote negative sign, so that's my bad. So let me rectify this. So I just rectify. Okay, so now it's fine, it's working fine. Alright, now what to do? We are going to simplify this function, and then we are going to apply the limit e power x, and in all these terms we are having ex common outside. So inside the bracket is 1 plus 1 plus x is left. So it is giving me limit x is approaching to 0 e power x upon e power x times x plus 2. So once this and this gets cancelled, so we are having now limit x is approaching to 0, we are having 1 upon x plus 2. Now once when I apply the limit, now I'm going to get a real number answer. Okay, so I'm going to get a definite answer. So applying the limit, we get nicely. Once when we apply the limit, we are getting half answer. So this is it. That's how we solve the stuff, and that's it. Now let's see another example which is going to handle 0 power infinity type. So let's see what it is. Okay, so this is another example. So once you see when we apply the limit directly on this function, so what kind of what form we are getting? So it is 1. Okay, it's not 0 power infinity, it's a type 1 power infinity. Okay, so it's a power infinity type. Alright, so 1 minus 1, so it is giving you 1 minus 1 upon 0, so it is giving you 1 power infinity type. So once you are having this thing, how you're going to handle such kind of case, or so how you're going to sort out this function, because you see this function is not having numerator or denominator stuff. Okay, so this is purely in an exponential form. So how to do, what to do? So you see, first of all, you just simply assume that let y is equals to this function. Okay, so first of all, we just write that originally this function is giving me 1 minus infinity type. We just write this and we remove this word. And now we are going to assume that let y equals to x power 1 upon 1 minus x. Okay, now we are going to apply the log at both sides. Okay, so once when we apply log at both sides, it is, we just have to apply any log you want. Okay, it could be log log, it could be a natural log. It's up to you, because in all kind of logs we are going to apply the same properties there, so we have freedom. So once when we do this, after that you're going to apply the limit x tending towards 1. As you can see that at the left hand side we are having ln y, so we are not going to apply limit over here on ln y. We just keep it going like that. The real work is going to be applied on the right hand side. Okay, because the left hand side is actually simply, it's a supposition work. So that's it. Okay, now what to do? I forgot to write my ln here. Okay, this is ln. Now we are going to use our log property, that log of x power n is n times log of x. That's the property of log. So we are going to apply this property here. Okay, so it is going to be limit x is tending towards 1. 1 upon 1 minus x is actually the power times ln of x. Yeah. Now when we apply the limit here in rough, ln of 1 upon 1 minus 1, so ln of 1 is 0 upon 0. So we are getting on applying the limit, we are getting this indeterminate form now. Okay, so from 1 power infinity, the indeterminate form is now switched to 0 upon 0. Okay, so that's it. Now we are going to differentiate our numerator and denominator, traditional work. So ln derivative of ln x, so derivative of log of x is 1 upon x, upon derivative of 0 of 1 is 0 and derivative of x is 1, so we are having simply minus 1, 0 minus 1 here. So it is now minus 1 upon x. That's what we are having. X is tending towards 1. We are getting minus 1 upon x left. And once when we apply the limit now, we are getting definite minus 1 answer. Okay, so L'Hopital's strategy is now stop. We will now apply the limit. Applying limit we get. So once when we do this, we're getting minus 1 upon 1 equals to 1. Minus 1. So this is it. We end up. Okay. I hope now you're getting familiar how different types simply ooze out and how you handle them. Okay, now the last example is going to deal with this type, infinity power 0. Okay, this is the horizontal 8. Alright, so let's see our next example. Okay, so there you go. So here, once when you apply your limit directly on this original form, what you're going to get is 1 upon 0 raised to the power tangent 0. Okay, so tan of 0 is 0, 1 upon 0 is infinity. So we are getting this type. Okay, what to do now? How we are going to get rid of this exponential type function? Of course, we are going to take log at both sides. First of all, we will assume that let y is equals to this function. Then we will take the log of it, and then we'll try to figure it out further ahead. So before doing that supposition, we will traditionally going to write our form, that this form on applying the limit is giving us this indeterminate format. And now we will assume that let your y is equals to 1 upon x raised to the power tangent x, and then we will take log at both sides. So ln y is equals to ln of 1 upon x power tangent x, and here we will apply our log property of xn, as I told you, this one. So this thing tells me that ln y is equals to tangent of x times log of 1 upon x, and 1 upon x is actually x power minus 1. Yeah, so here once again we are going to apply this characteristic 1. So it is going to give me minus tan x times ln x. Yeah, this is my ln now. Okay, and as I told you that in order to apply our L'Hopital strategy, we need function in the numerator and a function in the denominator. So what to do now? What is going to come in the numerator? What is going to come in the denominator? So as we know that tangent is the reciprocal of cotangent, so you can write tangent as 1 upon cot x. That's how we do. Okay, now you apply the limit at both sides. Limit x is tending to 0, ln y equals to negative sign outside, limit x tending to 0, ln x upon cot of x. Once when you apply the limit now on ln x and cot x, what you're getting, what you are going to get. So it is giving me ln of 0 upon cot x is 1 upon tan x. So for my a's, I just write it like this. Okay, so ln of 0 is giving you infinity, and tangent 0 is 0, so it is giving you infinity over infinity. So you see, this format on applying the limit is giving you an indeterminate form of infinity over infinity. We need to get rid of this situation. So we will differentiate our numerator and denominator nicely. So once when we do this, ln of x is 1 upon x upon cot of x is derivative of cot of x is negative cosec square x. Yeah. So once when we do this, now we are going to take a nice format. We will transform our cosec x as 1 upon sin x. So once when we do this, one upon x, and this is 1 upon sine square x. Okay, so it is giving me this minus and this minus become plus. So I'm now having limit x is tending to 0. I'm having sine square x upon x. Okay, so now what to do? Once when I apply the limit, now sine of 0 is 0 and x is 0. So I'm getting 0 upon 0 now. Okay, so this format is still indeterminate. I need to differentiate these numerator and denominator once again. So let's do it. So it is limit x is tending to 0. Okay, so derivative of sine square x is 2 sine of x, and then I apply chain rule on my function sine x, so it is going to give me cos x, and derivative of x is 1. Okay, so we are getting limit x is tending to 0, 2 sine x cos x. Now once when I apply the limit here, what I'm going to get? I'm going to get a real value answer, of course. So once when I do this, sine of 0, cos of 0, sine of 0 is 0, cos of 0 is 1. So I'm finally getting 0 answer, which is a definite real number. That's how we end up. So you see, you keep on continuing your L'Hospital strategy till finally you get rid from all kind of indeterminate forms. Okay, so once when you see that you are getting a definite answers after applying the limit, a definite real number, you will stop your work and you end up. Okay, not you end up, of course your work is going to end up. Okay, that's all for today, and if you find this video helpful, I humbly request you to subscribe my channel, hit on the like and share this video as much as you can with your friends and other learners, and don't forget to visit my website to see the further details if you are interested in having an online mathematics coaching with me. Take good care of yourself, study well, score good. Allah Hafiz.